Good evening, everyone. Is my microphone on? And welcome to Observatory Nights at the Harvard-Smithsonian Center for Astrophysics. We're very pleased that you could join us this evening. Tonight, we are going to be learning about what I think is one of the most fascinating projects going on at the Center for Astrophysics right now, and that is the Event Horizon Telescope. This is a virtual telescope that is going to unite facilities around the globe, including the Smithsonian Submillimeter Array, in a very bold attempt to photograph the black hole at the center of our galaxy. But wait, you might be asking the question, how can we possibly photograph something that does not emit any light by definition? And the answer is that we are actually going to be looking for the shadow or the silhouette of this black hole. And in doing so, we are going to put Einstein's theory to the ultimate test. Tonight's speaker, Michael Johnson, is an astrophysicist and a member of the Event Horizon Telescope team. He is also a member of the CFA's Institute for Theory and Computation and an inaugural member of the Harvard Black Hole Initiative. He joined the CFA in 2013, and prior to coming here, he earned his bachelor's degrees in mathematics and physics at the University of Southern California, and his PhD in physics from UC Santa Barbara. Please welcome Michael Johnson.
Well, thank you, Christine, for the introduction, and welcome everyone. I am so delighted to be able to share with you the excitement of this new project, the Event Horizon Telescope, which is really just coming online this year. And as Christine said, the goal is pretty simple. We want to make the first picture of a black hole. And a lot of you may recognize this image. This is from Interstellar. And this image, like every other picture you've ever seen, it is an artist's conception of what a black hole might look like. And so what we want to do is change that and really provide astronomical observations that finally put the theory of Einstein's gravity and the strong gravity regime near an event horizon on firm observational footing. So what I'm going to do is I'm going to start with just an introduction to black holes and try to motivate for you why we're so excited about the sort of science that we're going to be able to do with the EHT. And then what I want to do is explain to you how the EHT actually is going to work. It's not a conventional telescope, and so there are some different ideas that come into play and that allow us to push to these incredibly high angular resolutions that are required to make an image of a black hole. Then I'll show you some of our early science results and also give you a preview of where we might be over the coming years. So the story of black holes actually begins in the 1700s when John Mitchell wrote this remarkable paper. So he wrote this paper on the means of discovering the distance, magnitude, etc. of the fixed stars in consequence of the diminution of the velocity of their light, in case such a diminution should be found to take place in any of them, and such other data should be procured from observations as would be further necessary for that purpose. So as a tip, anytime you have such a succinct and punchy title, you know it's an important paper. Right. So what was John Mitchell talking about here? So Mitchell's idea was related to something pretty simple, and that's escape velocity. So let's say that you have something on Earth and you want to launch it into space. You know, if I jump, I fall back down to the Earth because I'm trapped by the Earth's gravitational pull. But if you launch it with enough velocity, then it's able to escape that gravitational field and go all the way to infinity. And so it requires this critical velocity in order to do that. Now, the remarkable thing here is that that velocity doesn't depend on how massive the thing you're launching is. It's kind of paradoxical. So to launch me into space would be the same velocity as you would need to launch a rocket into space or a bowling ball or anything else. Now, what Mitchell was thinking about is he thought, well, what about light? Incredibly, in the 1700s, they already knew that the speed of light was finite. And this is amazing. The speed of light is 186,000 miles per second. And even in the 1700s, they knew that it wasn't infinite. So that's another amazing measurement that was actually done by astronomers. So it's this recurring theme that we'll see of astronomers contributing to fundamental physics. So what Mitchell thought was, well, what if the escape velocity is more than the speed of light? Then photons won't escape, and the star, or whatever object you have, will become dark. So he envisioned these dark stars floating around the universe and just emitting no light. It was actually this incredibly visionary thing. And he said, well, maybe they'd be in binary systems. So what you'd see is a bright star, and it'd be wobbling on the sky because it's actually going in orbit around this other thing that you can't see. So it's this incredible, incredible insight. Now, to do this, what you have to do is you have to take a fixed mass and you compress it within a particular radius. And he calculated it. It's a very simple calculation. And you can try this out yourself. You just take twice Newton's gravitational constant, multiply it by the mass of the object that you're looking at, and divide by the speed of light squared. You can even just put this in Google, and it's a nice thing to try. So as an example, let's suppose that you want to make the sun into a dark star. It turns out if you squeeze it down to about the size of Cambridge, that would do it. That would make it so the speed of light wouldn't be enough to escape the star. So obviously that's quite, that would be an incredibly dense object. But the strange thing is that as you make bigger and bigger, black holes in this case, the density goes down. So if you were to fill the solar system with water, that would be enough to make a black hole. These incredibly large black holes that are millions or billions of solar masses actually have density that's, something like water. Okay, so the modern story of black holes started in 1915 with Albert Einstein when he published his theory of general relativity. And in this theory, he replaced the Newtonian idea of masses attracting each other with a new idea that masses curve space-time. Now, one consequence of this was that Einstein predicted that light would be affected by the curvature of mass. Light is bent by gravity. Now, you'll notice that Mitchell made the same assumption, and this actually goes back to Isaac Newton. But one difference in Einstein's theory is that he predicted that the curvature would be twice as much as the Newtonian prediction. And this was confirmed shortly after Einstein published his theory, and that's what catapulted him to be an international sensation, was measuring that curvature of light in gravity. Now, within just 2 months of publishing his theory, Schwarzschild, who was stationed on the Russian front, had found the first exact solution to Einstein's equations. So while he had a lot of free time there, I guess, and he worked this out. And what he worked out was the solution when you have a spherically symmetric static case. So basically a ball of mass just sitting there. So this applies to a lot of stuff. It applies to the Earth, for instance, and the sun, and also black holes. So one thing you can calculate with Schwarzschild's equations, for instance, is how fast your clock runs when you're on the Earth. It turns out your clock runs a little slower because it's sitting in a gravitational well than someone who's much further away. So this was an amazing contribution, and his solution depended on a particular radius, which is twice Newton's gravitational constant times the mass of the object divided by the speed of light squared. That's the same thing that Mitchell calculated. And so this is now called the Schwarzschild radius, and this is the radius of a black hole. This is the size of the event horizon for a static black hole. Okay, so next up, fast on the heels of Schwarzschild is David Hilbert. So Hilbert was a mathematician, but he was getting into the physics game, and he wrote an article that he humbly titled The Foundations of Physics. And one nice thing in this article is that he derived the first case that I know of, at least, of what a black hole might look like to a distant observer. So he took Schwarzschild's solution and he said, what if you have this object sitting there and you shine light on it and you allow those photons to pass beyond it? Well, it turns out photons that are sort of headed towards the black hole, they'll fall into the black hole. Photons that are far away will just be bent a little by the gravity, but they'll still make it to infinity. And so what you'll see if you're sitting far away from that is you'll see that the black hole is casting a shadow on that background radiation. And he showed that that shadow will have a diameter that's 5.2 times the Schwarzschild radius that we saw earlier. Okay, so up until this point, black holes had been kind of a theoretical curiosity, or, mathematicians like them. But I don't think, people didn't take them that seriously. But Chandrasekhar showed that if you have a white dwarf and its mass exceeds 1.44 solar masses, then what will happen is that the thing holding up the white dwarf, which is electron degeneracy pressure, it's a quantum mechanical phenomena, it can't actually sustain it anymore. And so at that point, it'll collapse down into a point. And this upset a lot of people. Now, black holes aren't this abstract thing anymore. We knew that there were white dwarfs. And so the question is, if you pile enough mass on, it seems like a black hole is inevitable. And so people sort of ridiculed this and gave him a hard time about this because they said there must be some law of nature that prevents that from happening. How could there possibly be this singularity in nature? And the last part of the modern story is with Kerr. In 1963, And remember, it took 2 months for Schwarzschild to discover that first solution for Einstein's equations. It took 50 years for someone to come up with the next step, which is, if it's not static, what if your black hole is there, but it's rotating? And the reason this is so important is that this completes the story of black holes. There's something called the no-hair theorem that says black holes are completely defined by just 3 parameters: their mass, their charge, and their spin. Now, it turns out that astrophysical black holes, if they exist and they have charge, they'll quickly pair produce near the horizon, and that'll discharge the black hole. So astrophysical black holes really just have 2 parameters, mass and spin. And now they're completely described by this metric called the Kerr metric. And I just love this quote by Chandrasekhar. He says, "In my entire scientific life, the most shattering experience has been the realization that an exact solution of Einstein's equations of general relativity provides the absolutely exact representation of untold numbers of massive black holes that populate the universe." It's just profound that this relatively simple equation I have here provides all the theory we need to predict the image of a black hole. And so this is an extremely firm prediction for us to test with these astronomical observations that I'll tell you about. So even until this point, black holes were still kind of, the realm of mathematicians and physicists, but they became a lot more tangible when astronomers got into the game. And it turns out that the best place to look for and really convince ourselves that there's a black hole is at our own galactic center. So here's a picture of the galactic center in X-rays and also in infrared. And if you look right at the center in X-rays, what you'll see is that there's a little lump of emission. Now, what this emission turns out to be is hot electrons that are bound to the black hole. So they have some temperature, and that's the region at which their binding energy from the gravity of the black hole exceeds their thermal energy. So it's this cloud of material that's defining sort of the outer boundary where things are beginning to fall onto the black hole. Well, maybe that's not so convincing. I mean, I wouldn't bet my life that there was a black hole there just from this image. But the thing that was the real deal breaker was when people started monitoring stars that were within this region. So zooming in, these are stars in near infrared, and many of you have probably seen this image. They've been monitoring these stars for the last 20 years with extremely high angular resolution, and you can see their orbits here. And you can see these orbits swinging around this unseen object right at the center there. There's absolutely no emission there, but these stars are stopped completely in their tracks when they get too close and they get flung away in these Keplerian orbits, again, just like planets around the sun. So by studying these orbits, you can estimate how much mass has to be sitting there in this unseen object. And the answer turns out to be about 4 million solar masses in this tiny region of space, and that is what's required to have these stars be flung around. So this is just an absolutely amazing measurement, but the closest approach of any of these stars is still about 1,000 Schwarzschild radii. And you'll notice these are still sort of, just Keplerian ellipses. These, this isn't probing this strong gravity region right near the event horizon yet. So the question is, what if we zoom in even further? What do we see when we get even closer to the black hole? So this is something that Bardeen started looking at in the 70s, and he extended Hilbert's calculation to the case when a black hole has spin. And what Bardeen showed was that to a distant observer, if you looked at a black hole that's being bathed by a bath of these photons, it'll again cast this shadow. And the amazing thing is that spin of the black hole doesn't change the shape of the shadow very much. It changes it by only about plus or minus 4%. And so we have this very robust signature of general relativity that we expect this nearly circular shadow, and its size is completely determined by the mass of the black hole, which we know from the stellar orbits. Now, since Bardeen, a lot of people have extended these calculations to more astrophysically reasonable simulations. So that center panel is one done by Avery Broderick. And what he looked at was, suppose you have an accretion disk around a black hole. Then what you'll see is a bright patch of emission on one side and a faint patch on the other. Now, what's causing that? So accretion disks near a black hole have to be rotating extremely fast. So it's rotating at almost the speed of light, and what happens is that on the side of the disk that's approaching you, the light gets lensed and beamed towards you. It's a Doppler effect. And on the opposite side, it gets Doppler deboosted, and that's why it's faint on that other side. And in addition to the bright patch and the faint patch, you'll again see that ring, and that's the same ring that was predicted by Hilbert and Bardeen and others. Now, more recently, what people have been looking at is full three-dimensional simulations of a black hole. So this is just one that's done by a postdoc here, Hodaka Shiakawa. And in this case, he's evolving a magnetized fluid around a black hole. And he's feeding in Einstein's equations and saying what's going to happen to this fluid as it's going. And you can see that these arms of plasma are getting sheared out by the differential rotation near a black hole. And in addition to all of this complicated plasma dynamics, you can also see, again, that bright photon ring that's determined just by the geometry of the spacetime. So again, this is our goal. We want to see this ring and put Einstein's theory to the test. So maybe I've convinced you that black holes are not difficult to see because they're black. Right? There's plenty to see if you have something lighting up the spacetime. They're hard to see because they're very small. So if you were to look over the entire universe, the biggest black hole in the sky, as seen from Earth, is Sagittarius A star in our galactic center. There are other black holes that are bigger. They have bigger event horizons, but they're further away. So the net effect is that they're smaller as viewed from Earth. The size of Sag A star is about the same size as if you took an atom and held it at arm's length. Okay? So the question is, how could we possibly make a telescope with enough resolution to be able to see something that's so small? To understand that, it turns out that we can draw some inspiration from ducks. So here's some ducks splashing around. They jump into a pond and they start kicking their feet furiously. They're stirring up the water there. And near the ducks, you'll see that the water is stirred up and turbulent. But further away from the ducks, you see that you have these outward propagating coherent wavefronts. You see that? You know, ducks stirred up, turbulent, far away, nice and coherent. So what I want you to do is imagine that you're sitting on the boundary of the pond, okay? And as those waves are coming to you, you're seeing the water slosh up and down. Here's the miracle. If you put people around the boundary and blindfold them so they can't see the water, all they can do is feel the sloshing up and down. They can reconstruct the positions of all the ducks. Okay, so let's break this down a little bit. You thought I was kidding about the ducks. No, we're doing this. So on the left here, we're going to imagine some ducks that are close together and they're splashing around. And on the right, we're going to put some ducks that are further apart, splashing around. So let's look at that left case. Let's let them go. Okay, so they splash around, waves propagate away. In the middle, it's turbulent, irregular. You see these nice coherent wavefronts, and now you see it sloshing on that boundary. You see that? So it's a nice regular sloshing, and you could imagine if you and your neighbor are sitting pretty close to each other on the pond, you're going to see it sloshing about the same. Okay, what about the right? So now these ducks, they're a little further apart. Let them go. Waves propagate away. Nice coherent wavefronts further away. Still sloshing on the boundary, but now you and your neighbor, if you're sitting further apart, see different sloshing. It's not the same. You see there's a lot more fine-scale structure around the boundary of the pond in that second case. Okay, so it turns out there are sort of two things that we can look at here. One is the amplitude of the sloshing. So let's say you don't have any friends, and you're just by yourself. No comment. So you're just by yourself, and you're seeing the water slosh up and down. It turns out that doesn't tell you about whether the ducks are close together or far apart. That just tells you how many ducks there are and how violently they're splashing around in the water. But if you're able to look at the coherence length of the splashing and say, how much does it change? How far away does my neighbor have to move so that we start seeing patterns that are uncorrelated with each other? That's telling you about whether ducks are close together or far apart. So let's just watch the movies one more time at the same time. And you can see in these two cases, you'll see that the amplitude of the sloshing is about the same in the two. But on the right, there's all this small-scale structure. And on the left, you and your neighbor would be seeing pretty much the same thing going up and down. Okay, so we are not studying ducks, but it turns out that there's a close parallel. So instead of ducks, what we have are electrons gyrating around magnetic field lines. And instead of water, what they're doing is they're sending out these ripples of electromagnetic waves. And what we're doing is we have telescopes on the Earth, and that's like sitting on the edge of the pond. And these telescopes sample the ripples of these electromagnetic waves. And by comparing the ripples at different telescopes, we're able to infer what the structure of those electrons are, whether they're close together or far apart. And we're able to make pictures of where the electrons are. That's how we make an image of the source. So this is a technique. It's called radio interferometry. It was pioneered by Martin Ryle, who won a Nobel Prize for it in 1974. And this was the first Nobel Prize ever awarded for astronomy research. Okay, so why would anyone ever do this? To understand that, I want to put it in the context of how it relates to ordinary imaging. So for ordinary imaging, the angular resolution you get depends on two things. It depends on the observing wavelength, and it depends on the size of your telescope. Okay, so bigger telescopes have better resolution, and shorter wavelengths have better resolution. So just for context, the human eye has an angular resolution of about an arc minute. Now, many of you will probably have seen a picture of a radio telescope. Radio telescopes can be huge. They can have 100-meter diameters or more. It turns out your eye has better resolution than they do. And this is because their wavelengths are so much longer. So radio telescopes are not great at angular resolution. Optical telescopes, on the other hand, are observing the same wavelengths as your eye, and they're much larger. So they can see down, 1,000 times better. They can see scales as small as 50 milliarcseconds or so. So what about interferometry? So the magic of interferometry is that your resolution doesn't depend on how big your telescopes are. It depends on how far apart you can put them. So instead of making bigger and bigger telescopes, all you have to do is spread them as far apart as you possibly can. And longer baselines, so a baseline is the line joining a pair of telescopes. And the longer you make that, the higher resolution you have. But there's a price to pay for this, and that's that interferometers don't make images directly. Okay, and the way that I like to think about it is in terms of music. So each baseline, each line joining a pair of telescopes, just samples one spatial frequency of your image. And that would be like, if your image were a song, it'd be like each baseline just hears one note. So if you want to piece together the whole image or the whole song, what you need are many, many different baselines, both long and short, and you can put together all that information and synthesize an image from it. So in this case, we have 4 telescopes. With 4 telescopes, you have 6 different baselines. Each of them has different length and different orientation, so they all hear different notes, and that could be put into an image. Okay, so I want to make this a little more intuitive for you. So we're going to do, an interactive activity. What I'm going to do is I'm going to play a song, and I'm going to let you hear the song as though you were an interferometer. So we're going to start with just two telescopes. 2 telescopes, there's only one line between them, so they only hear one note. So at the beginning, you're only going to hear one note of this song. And as we go on, I'll add more and more telescopes. So you'll hear more and more frequencies, and eventually, hopefully, you'll recognize the song. So low frequencies are to the left here, high frequencies are to the right. The red line is telling you which ones you're hearing at any particular time. And the 88-key piano is on the bottom. It's kind of a reference for what these frequencies mean. Okay, so here we go. What I want you to do is when you recognize the song, just go ahead and raise your hand and keep it up. So here we go. So now you just hear one of the notes in the song. Okay, so that's how interferometry works. And one thing I just want to draw your attention to is, at the beginning, when you only have 2 sites or 3 sites, there's just not enough information to know what's going on. But it's pretty amazing that there can be a lot of gaps in your coverage, and your brain can fill in the holes and still tell you what you're listening to, even though you're missing that information. It's sort of like if your glasses are pretty dirty, you can still see fairly well. And that's the principle of interferometry, that we don't build one big dish as big as the Earth. What we're trying to do is selectively sample, add sites, and build enough coverage that we can fill in the missing gaps using algorithms. One other thing is you'll notice some people got it soon, other people took longer, some people never recognized it. No judgment. And And that's related to the concept of prior information. Okay, so some people, maybe they're very familiar with the song and they were expecting to hear something like that. And maybe some other people, they'd never heard this song before, and what's going on? And that's fine. We have the same thing for making interferometric images. We want to have enough flexibility that we can still see things that we're not expecting. Of course, we could just, expect to see the shadow of a black hole, and then you don't need much data to match it to that. But what we want to do is have enough sites so that we can still see things that, we absolutely weren't expecting to see. Okay, so pulling it all together, this is the Event Horizon Telescope. And what the Event Horizon Telescope is not one telescope, but it's a collection of telescopes all over the Earth. And what we do is not build these telescopes, but to install equipment at them so that they can act together as part of a single interferometric array. So typically what this means is that we have to install an atomic clock there, because they have to be perfectly synchronized so that we can compare the sloshing electric fields. And we also install very high frequency recording equipment. So the sloshing waves we saw before had a period of something like a second. They're going up and down fairly gently. The waves that we're looking at, the electromagnetic waves, would go up and down billions of times a second. So each site has to be recording data at rates of gigabytes per second. And our observations collect petabytes of data over a single observing run. Those are then shipped to a supercomputer, which is the last ingredient in this telescope. And the supercomputer is where all this data gets combined and compared and processed, and that's how we finally make images. Now you can plug in the numbers. We're observing at a wavelength of 1.3 millimeters, and we're building a telescope, an interferometric telescope as large as the Earth. This gives us an angular resolution of about 20 micro arcseconds. This is thousands of times better than the Hubble Space Telescope. And here you can see this black hole image from before, and you can see the resolution of the EHT when it's done will be enough to make this picture of the photon ring. So that's how we achieve the resolution. Now you might be concerned. You'll notice we still don't have that many sites. And when we were listening to that song, even with 6 or 8 sites, I don't know if anyone was able to recognize the song at that point. So how could we make a picture with only this many telescopes? It turns out there's one more part to the story, and that's that we make the Earth part of our instrument. So the idea is the following. As the Earth rotates, the baseline joining every pair of telescopes is changing as a function of time. So it's actually a bit more than what I said. It's not that every pair of telescopes samples one frequency. It samples one frequency at each time, but then the Earth rotates them, and so it's allowing each baseline to sample many, many frequencies for us over a night. And this is the last part of the story. By adding all this additional information and using the Earth as part of the instrument, that's how we're going to get enough frequency information to go from these measurements to actual pictures of a black hole. Okay, so what have we done so far? So
at any given point, there's a very narrow window where all sites are seen can face the same direction at the same time.
That's right. So it turns out for this, the question was at any particular time, there's maybe only a few sites that can see the source, and so a key question is you need mutual visibility. Looking at the sloshing of the waves doesn't do you any good if you look one day and your partner looks the next day and then you compare notes. You have to be looking at the same time, and so we can only use those baselines where both sites are seeing the Earth. And so yeah, absolutely, there are some times where it's contributing a lot of information and other times it's not. But the great thing is that we can take all of the information and we can feed it into an algorithm that uses it all over the whole night of observing. So we don't take much of a loss there. So far, we haven't had the entire array working. All we've had is 3 sites for most of our data so far. But I just wanted to give you a sense of what we can learn with even just those 3 sites. And so this now is it's a figure. This is straight out of one of our papers. So if you see a future EHT paper, you'll be able to read it and understand these figures that are a mystery to most of the community, the astronomy community. So what's being shown here is on the x-axis, it's the length of the baseline. Okay, and so we have a triangle. It's got 3 legs, so there are 3 little bunches of points. On the y-axis is shown this thing. It's called the correlated flux density. That's just a measure of how correlated the fluctuations are at these two telescopes. So when the telescopes are close together, they see a lot of correlations, and what we're seeing here is that when we move them far apart, the correlations fall. So in this particular case, the two telescopes in California and Arizona saw fluctuations that were almost exactly the same. But comparing the telescopes in California and Arizona to Hawaii, they're seeing things that are quite different. Now, why is this useful? Well, just like the ducks, by seeing how far apart you have to move on the boundary of the pond, that's what told you about how spread out the ducks were. And so in this case, we can just take and find the scale on which this falls, and that gives us the size of the source we're looking at. And in this case, it tells us that the source we're looking at is only about 4 Schwarzschild radii across. Okay, so I just wanted to come back to something we saw earlier, which was that X-ray image of Sagittarius A star. So it's this sort of featureless blob that defined all of the accretion flow of Sagittarius A star. That extended over a range of about 100,000 Schwarzschild radii. 100,000. And nearly all of the emission is actually coming from something that's 4 Schwarzschild radii across. So it's this tiny speck at the middle of this vast accretion system that's pumping out all of this energy. It's incredible. The engine is the black hole itself. The engine is coming from right near the event horizon. Now, the danger, of course, is that we don't have much information, and we have to be careful. The danger of sparse information is that even if you just have a little bit, if you become too confident, you can kind of make a fool of yourself. So it's like the parable of the blind men studying the elephant. Each of them only has a little piece of the puzzle and is inferring something that's quite wrong. So in our case, this is that same data, but now I'm just putting 2 models through it. Okay, so the top model is the best fit Gaussian to this data. So it's saying, suppose that our source is just a Gaussian blob on the sky. And you can see that that fits the data just fine. And the model below that is the best fit ring, more like what we're expecting to see for the black hole shadow. That also fits the data. So you can see that with only 3 sites, there's just not enough data to distinguish even among simple toy models like this. And this is why we have to be careful. What we need to go to more, to actually take this to an image or even constrain these models is just more sites and more frequency coverage. But it turns out you can do a lot even just by increasing sensitivity. So I'll show you, this is just some data from 2013. And here we increase the sensitivity of our array and also the calibration procedures. This allows the telescopes to point further down at lower elevations. And this allows them to watch Sag A star over more of the rotation of the Earth. So this fills in more of those frequencies. And you can see even with this bit of extra information, we can already confidently rule out that Gaussian model. It doesn't match the data at all, but interestingly, the ring is still providing a pretty good fit. So these are just the first steps. It turns out the EHT can also see something that we can't, and that's polarization. So these sloshing electromagnetic waves, it turns out they can slosh like this, or they can slosh like this. They can slosh in different directions. And that determines something called the linear polarization of the electromagnetic waves. The reason we care about this is because I said the radiation we're seeing from Sag A star is coming from electrons that are zipping around these magnetic fields. And those are producing polarization that traces out the magnetic fields for us. So ultimately, the EHT will be able to make images of the polarization, which is the same as being able to make images of the magnetic fields near Sag A star. And this is important because magnetic fields are everything in the story of a black hole. I just want to give you 2 examples. So first of all, it's pretty hard to fall into a black hole. This is confusing. People think of black holes like a vacuum cleaner, just sucking stuff in. But it's not. If the sun were replaced by a black hole, the Earth would just continue happily orbiting around. If you throw a tennis ball around a black hole, it doesn't fall in. It'll just go in orbit around the black hole. It'll just sit there. It doesn't suck that in. And so actually, it's a question of how can these black holes be such efficient engines at the centers of galaxies, converting gravitational energy into this radiation, if they don't have some mechanism for actually pulling the stuff inward to convert that gravitational energy. So the mechanism that we think is responsible for pulling material into a black hole is actually turbulence that's driven by magnetic instabilities in the accretion flow. So what we're expecting to see is a very irregular and turbulent accretion flow And that will solve the riddle of how these black holes are able to swallow material so effectively. There's another interesting thing about black holes, and that's we think of them as kind of endpoints for energy. You know, stuff can fall in and then, you know, we can't touch it. It's gone forever. But it turns out that if a black hole is spinning, you can pull out almost 30% of its energy by spinning down the black hole. And one way to do this is with magnetic fields. So if you have magnetic fields that are threading a black hole, what will happen is that the black hole will twist those up. It's like twisting in like a motor. And you can slow down the black hole in this way. And it's thought that maybe slowing down black holes and pulling out their energy in this way might be an energy source for some of the brightest extragalactic jets in the universe. So these types of questions are all things that we can do once we're able to make polarimetric images with the Event Horizon Telescope. Now, of course, we only have 3 sites. We're not able to make pictures yet. But one thing we were able to do is solve one riddle, and that's that people have been able to measure that Sagittarius star has about 7% polarization for the last decade or so. But the question is, why is it so low? The sort of theoretical prediction for the polarization would be more like 50 or 60 or 70% polarization. So why is it so low? And it turns out that there are 2 possibilities. One is that it's intrinsically low polarization, and that the polarization field is pretty uniform. But another possibility is that it's actually highly polarized, but the magnetic fields have a lot of structure in them. And that structure will cause cancellation of the polarization that you see if you don't resolve the image. If all you do is measure the net effect of the polarization, there can be cancellation across the image. So with the EHT, we were able to resolve the polarization structure and show that there have to be ordered magnetic fields near the black hole. But even more than that, we were able to see that these magnetic fields are dancing around rapidly as a function of time. They change on timescales of an hour or less. And so we're starting to see these intense dynamics of the magnetic fields near a black hole and see that in real time. So just to summarize kind of the key results of the EHT to date, you know, these are what we have with actual observations and the statements we're able to make. You know, first, we're able to say that the energetically dominant emission from this black hole is coming from a region that's about 4 Schwarzschild radii across. You know, very close in size to the expected black hole shadow, and, you know, comparable in size to the event horizon itself. We're also able to detect ordered magnetic fields near the event horizon and see how they dance around as a function of time. A third thing that we're able to do, which I didn't have time to mention, is that we're able to study the phase of the signal. So if you and your partner are sitting around a lake, you might see that, oh, well, we're always oscillating kind of in sync, except, you know, you're always low while I'm high, or something like that. So the relative phase of that signal allows us to say that there has to be a symmetry in the image of Sagittarius star. It actually can't just be a featureless Gaussian blob or something like that. There has to be asymmetry like that bright and faint patch that we saw earlier. And so the next step, of course, is to collect more and more information and go from these sort of rough statements to actual pictures. So to do that, what we have to do, we have to add those other sites to the array. And so I just want to show you this figure that shows the expected frequency coverage that we're going to have this spring when we take data. Okay, so on the left there, that's what we had in the past, with just 3 sites. And each of those blue curves is actually just one pair of telescopes. And the reason it's a curve in this frequency coverage is because of the rotation of the Earth. It's tracing out different frequency components of our image. On the right is the frequency coverage that we expect this April. Okay, and you see there's a world of difference between these two, and that rightmost one is the one where we might finally have enough information to make the first pictures. So I want to emphasize this is not data, but what we can do is we can simulate observations. So on the left here, this is a simulated image like the ones I showed you earlier from these simulations where they evolve in 3 dimensions, this magnetized plasma around a black hole. And then what we do is we sample data according to what we expect for the sites that are going to participate this spring. And we add noise that we expect that we're going to get. And so we try to make as realistic a synthetic data set as possible. And then what we do is we've developed imaging algorithms that take that frequency data and we convert it to a picture. And you can see here the types of pictures that we think we'll be able to get this spring. And so features like the bright on one side and faint on the other, That's the sort of thing that we're hoping to be able to see. And even these distinctive features like the photon ring surrounding this black hole shadow. If we're lucky, if the weather is good and the sites perform well, we have a real shot at doing this just in the next few months, potentially really having images like this by the end of the year. Okay, so what's next? It turns out we don't have to stop there. We don't have to stop at a static image of a black hole. Another very special thing about Sagittarius A star is that it evolves very rapidly. So to give you a sense of this, the innermost orbits around Sag A star have timescales, have orbital periodicities somewhere between about 4 and 30 minutes, depending on the black hole spin. So if the black hole is just static, like the Schwarzschild solution, the periodicity is going to be about 30 minutes. But if it spins up the black hole and you're moving in the same direction as the black hole spin, you get dragged along, and that's why the periods are shorter. So this is pretty crazy. In astronomy, most of the time we're looking at things in the sky that don't change over time. We're lucky to see things often that change over a lifetime. And here we're talking about something that changes on timescales of minutes. And so when the Event Horizon Telescope is complete, we might have the opportunity to actually watch a black hole in real time and actually see the dynamics of material approaching the event horizon as it's happening. So I just wanted to show you one example of this. On the left here is a simulation of a hotspot around Sag A star. Okay, so this is sort of like, you can imagine like a solar flare or something. Some impulsive event goes off, boom, it heats up electrons, and those are trapped in an accretion flow. And so they'll be pulled around the black hole in these orbits. So you'll see that go. Now this doesn't look like just one spot orbiting another spot, because the black hole is also lensing all of the emission that's coming off of it. So even when it's behind the black hole, you're seeing the light being lensed around above and below the black hole. And you can even see on the opposite side of the main spot, you can see a secondary image where photons are lensed back behind the black hole and then come around to the observer. They follow these curved trajectories. Now in the middle, we've done that same type of exercise that we did in the previous figure, where we've sampled data from this simulation, and then we take that data, corresponding to types of observations we think we might be able to get, and we try to reconstruct images. But in this time, we're not reconstructing a single image, we're actually trying to reconstruct a movie. Okay, so we're trying to link together all of that frequency information into enough information to be able to reconstruct this time-dependent image. And you can see on the right, that's the actual relative speed of the Earth rotating as a function of time in this simulation. So this would just be tremendous if we could actually reconstruct this. And the thing I want to emphasize here is that this work was done with a lot of really talented people here, a lot of grad students and postdocs. And what you'll see when you look at these people is that they're not all astronomers. Some are from physics. We have an expert from computer vision. We even have mathematicians working with us. And one lesson that we've learned here is that we can't just draw on the expertise of the astronomy community to do the sort of science that we want to do. If we want to really push these imaging techniques and push what we can do with astronomical instrumentation, we have to draw on the expertise of many different fields. And so this is just a picture from one of the first imaging hackathons that we held. But what we're doing now is we're even releasing synthetic data sets online, and we're having public imaging challenges. So I invite all of you, or any of you, if you're interested, download a data set. Maybe you have ideas about how to make images. Maybe you work in signal processing or computer science, or maybe you just have a great idea. And so you can actually, go to this website, download the data sets, make images, participate in challenges, and you can really be part of this quest to make the first image ever of a black hole. So absolutely get involved. And just to kind of end on the same theme, I just want to emphasize the Event Horizon Telescope is not a project that came about because someone had a great idea working in isolation and wrote down some equation or something like that. This is a team of a huge number of dedicated engineers and scientists and astronomers all working together. These are all people who got together just a few months ago to discuss EHT science and try to get the instrument ready for this April for the observations. And down below, I've listed a few locals who are key contributors to a lot of the science that I've talked about already. So I just want to emphasize, this is a group activity. There's no prototype for science. We started with a bunch of pictures of sort of old white men, and that's just simply not true anymore. There's a lot of diversity in the people who contribute, and I hope that we'll have images like this to share with you in the coming year. So thank you for your attention, and I'm happy to answer any questions.
I think this is such an amazing place. This is the kind of stuff that we do. Hello. Okay. So, question and answer time. Questions? Yes.
All right, I'm trying to reconcile something.
Sure.
Maybe it's just me. Okay. I understand the analogy with the pond and the ducks. Okay. But what I'm getting at is I also understand that you have your telescopes spaced all around the Earth. However, it seems that the black hole is so far away from the Earth that it would be the equivalent of all your telescopes stacked, in one little spot on the edge of the pond.
That is exactly correct.
If that's true, you said earlier that to notice the differences, you'd have to have your friends stand further away. So if we're in that one little spot of the pond, even though you have multiple telescopes, it just doesn't seem like far enough away. They're far enough away. You need them on every planet, around the black hole.
That's right. You're absolutely right. So first of all, a couple differences. It is true that the boundary of the pond. Is there feedback there? Well, anyway, the boundary of the pond does contain all the information about the three-dimensional picture of the ducks. Okay, we're not able to get the three-dimensional picture of the black hole. All we get when we're sitting so far away, basically just seeing a two-dimensional projection, is that two-dimensional image. So that's the first hit we take because we can't spread telescopes around different galaxies. Or, not different galaxies, but yeah, absolutely. And the other part of the question, the answer is it's just magic. It's one of these things that it's easy to give glib answers for these things, but fundamentally, the guy who came up with it and really implemented it got a Nobel Prize. It's just this profoundly beautiful idea, and the fact that it actually works. Maybe another way to convince yourself of why the Earth is big enough, let's say, is if we go back to the pond example. We were thinking about sort of sitting as moving apart, where you'd start to see different sloshing around, and kind of the way that you would visualize that is in terms of the wavelengths on the edge of the pond. In interferometry, the thing that matters is the distance between your telescopes in wavelengths. Okay, and so we're observing at 1.3 millimeters. So the distance between our telescopes is actually billions of wavelengths. It's basically the diameter of the Earth divided by 1.3 millimeters. And I think that's where, visually it's just hard to imagine, a separation of billions of wavelengths around the edge of the pond, but that's how we achieve such high resolution. It's a great question.
Okay, I understand.
Have you thought...
There's a gentleman in the back.
I'm not an astrophysicist or an astronomer. I just have interest in this. So, if you can find a pattern for these wavelengths, can you eliminate time? Meaning, can you use the Earth's orbit as your diameter, as you observe at different points in time, and you can expand that diameter?
That's a really clever idea. There might be astrophysical sources where that's possible. If there was an alien civilization that was shining lasers at us, that would work, I think. Don't quote me on that. It turns out that astrophysical sources basically emit white noise. It's like, I guess the television analogy doesn't work anymore, but they're just emitting this incoherent hiss of noise towards us. Okay, and so instead of, the picture had 4 ducks, right? Whereas the number of electrons zipping around these fields, all doing their own thing, is uncountable. And so the signal that I see right now is completely incoherent relative to the signal that I see in a second, much less a day or a month or a year or something like that. And so because these sources are emitting this incoherent noise, that's why it's critical that each site be able to see Sagittarius star at exactly the same time, and why we need atomic clocks. Because if you shift your signals even a little bit, all you see is completely incoherent signal between different sites.
Gentleman over here, and then there over here. Go ahead.
Have you thought of using the moon as a reflection surface?
As a reflection surface?
Yes. Just a
well,
thought.
well, the moon is great as a station in the interferometer, right?
Okay.
You get a great big long baseline. You can put telescopes on the dark side of the moon to shield them from radio interference. There are proposals to do this. A better solution, I think, is to launch telescopes into space and you put them in orbit, and then they trace out lots of frequencies for you because they're zipping around and you're doing lots of different baselines. It's even better than rotation of the Earth. And this has actually been done. There are telescopes in space. Well, there's a telescope in space doing interferometry right now. It's called Radioastron. But they haven't currently been able to do them at such high frequencies as the Event Horizon Telescope. And so the frequencies that they look, Sagittarius star is actually obscured by scattering. Well, that's a long, different story. So I mean, the short answer is, yeah, moving to the moon and moving telescopes into space, it's the future of interferometry. It will happen. The idea of using reflections off the moon, that I'm not so sure about.
The reason I'm asking is just that ham radio, we bounced off the moon. And I'm thinking, if light from Sagittarius can bounce off the moon, I wonder if that would give you something, more piece of data. You look at the moon.
In the early days of interferometry, they would use reflections off the ocean, I think,
Oh, okay.
for the same idea, and it was tremendously successful. You can do interferometry with just one telescope. I've never heard of someone doing it with the moon. It seems like a great idea. I'm not sure if there's any fundamental reason why that can work.
Just a thought.
Yes, sir.
Yeah, so I understand the simultaneity of the telescopes on each baseline. How do you put together the picture when you're using different baselines at different times?
Yeah. So there's an easy answer and there's a hard answer. Okay, here's the easy answer. I cheated a little when I played, the song for you, because the song is changing over time. So if you know the frequencies at one time, that doesn't necessarily, you can't just smoosh all that information together, right? And so that's why you need simultaneity of measurements. A more accurate representation would be if I just played one chord for you. And that didn't change over time, and that's why you could collect information from different times, and you wouldn't need the measurements to be simultaneous. And that's the analogy if you have a source that's just static on the sky. That's the case for basically every source in interferometry except Sagittarius A star. And it's only because it changes so fast that it breaks this assumption of a static source that allows us to just integrate data and collect it from today to tomorrow and so forth. And so this is why we're trying to develop these techniques that pull it in and synthesize movies. It's a completely new regime for interferometric imaging that no one's ever had to worry about before. But it's a major problem, major difficulty, and download some data sets and help us solve it.
Do we have any questions up in the balcony? Oh, yes. Right. Yes, ma'am.
Sorry, I'm also not a physicist, but I was wondering, in your analogy with the pond, you have this beautiful pond that has nothing but the ducks in it, but I imagine in space, just as in the pond, there could be, any other objects in it that would kind of mess up the pattern that you or your neighbor would be getting because there's a stone or there's some flower or whatever there is. How do you account for anything in the way between the black hole and us, and how is that changing the waves that we're measuring?
Yeah, that's a great question. So telescopes, they have these parabolic dishes. That does a lot of it for you because it's focusing so that most of the radiation you're receiving is just from one region of the sky. Okay, even with that in place, when we take a signal, only about 0.01% of it is coming from Sagittarius A star. Most of it's coming from other stuff. Most of it's coming actually from thermal noise, within the telescope itself. A lot of it, you saw also the galactic center. We saw that picture of the galactic center. There's all sorts of other stuff going on there, right? So the question is, why is the signal we're looking for not completely dwarfed by that? And so the answer is, it is completely dwarfed by that at a single telescope. It's like if you're sitting on the pond, you see all this sloshing around, that's what's dominating what you see. But when you compare that with what your neighbor is seeing, let's say that you take one telescope and you take a second telescope and you make the interferometric baseline there. That baseline has a particular angular resolution that's extremely small. And so what that does is it filters out everything else. That, even though each telescope sees everything else, that baseline doesn't. So it's filtering out all the other stuff, and all it sees is this incredibly compact emission coming from the galactic center. Everything else is too smooth, and it's the interferometer is blind to it. So that's kind of the trick. But yeah, great question.
Chris.
I actually have a question from Julie, who was unable to make it because they're having car issues. She's the one who has the YouTube channel that Christine was talking about before. She asks, with all the telescopes involved, and I'm going to assume this is when the project is fully underway, what is the maximum number of telescopes that can look at an object at one time with good visibility due to the Earth's rotation?
Good visibility. So yeah, so I go to okay, so I cheated again a little, as see I have no shame about. This is the Earth as viewed from an astrophysical source. It's not the Earth as viewed by Sagittarius A star. So Sagittarius A star is actually a further south in declination, and it can't see Greenland. So you can let the Earth spin all day and never sees Sagittarius star. The South Pole, on the other hand, always sees Sagittarius A star. So that's a nice benefit of the South Pole. So the best case scenario with these particular sites is that we'd have, whatever that is, 7 sites that could see Sagittarius A star simultaneously, or at least near simultaneously. So 7 sites is kind of our prime goal. It's actually a bit more than that. Some of these have 2 telescopes. So in Hawaii, there are 2 telescopes that are right next to each other. One is actually an interferometric array, just like the EHT, but on a smaller scale, called submillimeter array, that's run through the Smithsonian here. And the other is called the James Clerk Maxwell Telescope, which is the single big dish. They're both there, and we take data from both of them. So we have this short, little tiny baseline between them, and then we get joint baselines everywhere else. So if you include those, we might get as many as perhaps 9 or 10 sites that can all see Sagittarius A star at the same time. And what we'd love to do is to develop some sort of smaller dishes where we could sprinkle them over the rest of the world, maybe deploy another half dozen or something like that. And that's probably what's needed if we really want to make moves to black holes, is to add that additional coverage. So yeah.
Thank you.
All right. Yeah, I have one up there. Let's make this the last question and a really good one. No pressure.
Unfortunately, just to clarify my question, I was wondering, is April the date you're hoping to have the next 1 or 2 online, or is April the date you're hoping to have all 9 online?
Right. So actually, all of these telescopes have now been confirmed to be operational. So we've done commissioning observations where we observe which is 1 or 2, and we make sure all the equipment works and everything. April is this magic date where they're all coming together, they're all observing at the same time for the first time, and that's why it's so special, is that we think, that's when we finally have enough coverage that we'll really be able to make pictures of black holes. So yeah, so this is it.
Okay. I think that's a good point to end on. We were talking about the future of this project, so let's thank our speaker again.